Thanks, Blake, and for the intro. And thanks to you all for coming out to hear me talk about rocks on this very cold morning. I appreciate it. When Blake first asked me to come speak to a bunch of creatives, I really had my doubts. I'm used to speaking to an audience of peers or members of the general public on the science of climate change. But then I figured actually it was kind of perfect because I'm a rock star, honest to God. So that having said, joking aside, what I really want to talk to you about today is the art of doing science. And I'll bring some visual imagery that has captivated me over the 20 years of doing what I do in climate science, and I hope inspires you, as well as teach you a bit about how I listen to the rocks and the story that I try to bring forward locked in these rocks. So first, we'll take a trip to the equator. This is my research site, Christmas Island, in the middle of the Pacific Ocean. And what you see here, well, first I guess we should all take a deep breath and breathe in the warm air. Feeling warmer already? Maybe? Okay. Pictured here, you can barely see them. These are rocks here lying on a beach at Christmas Island, and they look like brown, gray, black rocks. These are actually thousands of years old, and they are the remnants of corals that grew in the ocean thousands of years ago that have been lying on this beach. They each contain a story of climate from the period in which they grew, which I'm going to extract, and the story I'm going to tell to you today about the climate history in the middle of the Pacific Ocean and how it's changing today. This general field of work is called paleoclimatology. So this is a big word. If you learn nothing else today, now you know, another fancy word for your vocabulary. This is the study of reconstructing climate with geologic archives. So we do this with ice cores, we do this with tree rings, we do this with corals. My specialties are in the tropics because I like being warm. So my name tag said hot, hot, hot. So that's my specialty, and specifically interested in these very remote, most beautiful places on Earth. That's really where I want to hang out. So one might ask, it's fair to ask, how do you possibly get to be a paleoclimatologist? How did you end up there, of all places? It is a niche study. There aren't many paleoclimatologists in the world. So how did that happen? And it all starts when I was 12 years old, when I was accompanying my sister, who was studying geology at University of Massachusetts. And I was just sitting there waiting for her to finish. It was a snow day or something. And she put a thin section of kimberlite under a microscope and just let me look at it for a while. And this is indeed a thin section of kimberlite, which is a rock that is, all rocks in thin section are incredibly beautiful. And not only did it have some resonance with me because I share a name with it, but it also is the host rock for diamonds, which just captivated me as a 12-year-old. I thought, that is the coolest thing. This rock tells a story of its history, of the entire planet's history. And I became captivated by the thought that rocks could actually talk, although I wasn't able to understand their power until a lot later. So however, I went to college, and like most people who get to college, you think, oh, I'm going to be a doctor. I think everybody gets to college saying, oh, maybe I'll be a doctor. And I was on a pre-med track, and I took organic chemistry, and I took all these science courses, which were fairly easy for me. It was fine. That's why I'm a scientist today. But I wasn't really interested with a passion for that. And so the summer of my sophomore year, I applied to 19, count them, 19 medically related internships so I could spend my summer doing something related to my chosen profession. And I applied to one oceanography internship at the Scripps Institution of Oceanography in La Jolla, California. And guess what? I got into none of the medical internships, okay? None of them, yet I was accepted into the oceanography internship, which speaks to the kind of student that we allow into oceanography. Can't make it in the medical field, but joking aside, it was wonderful. It was life-changing, literally. And this picture here, I think, is another beautiful image from geology. This is a picture of a sediment core where you see, this is an ocean sediment off the coast of Santa Barbara, and you see summer, winter layers going back in time. And I spent that summer, my sophomore year, studying these sediment layers, trying to reconstruct climate from these particular sediments. And it, again, captivated me. How can rocks talk to us? How can we bring their message forward? And when I was studying in graduate school at Scripps later on, I would recognize that climate change is upon us. The earliest evidence is here. And if we take this back, we're going to learn a huge amount about natural climate variability and the trends that are going on today and put those in context. So I went to graduate school and I started studying climate most generally. And I found myself, this is another strange twist of fate, life is so like that. Life is full of so many twists of fate that determine where we are. I found myself on a yacht owned by the Prince of Saudi Arabia going down to the equator, okay? That's another story for another time. But yeah, it was great. There was blue cheese and cold beers and in bidets. It was crazy. And we found ourselves at the equator, and I found myself staring at images like this off the deck. And obviously, these places are exceptionally beautiful. They are one of a kind. They are uninhabited. It's very easy to fall in love. And that's exactly what happened to me. It was like a bonk on the head. That was it for me. I was done. And I decided to continue studying here, and I had to find something to do. And I looked around, and I saw these ugly rocks lying around. And I thought, I wonder what those rocks are. Kind of like rocks. And I like understanding what the climate signal is in them. And these are corals, actually. These are fossil corals. These are corals that grew hundreds to thousands of years ago that contain a climate record locked inside their skeletons. And this has become my niche in the field of climate science, bringing these rock records forward and bringing them into the context of current climate change. So this is my muse. This is a very ugly muse to you, perhaps. This is another image of a fossil coral that's growing, that grew, in this case, 700 years ago. And it contains within it this record of climate. This is one of the climate records I will show you later on. And so first we have to go there. We have to do, this is the Indiana Jones bit of what I do. I get to scuba dive with a huge 100-pound hydraulic drill, and I don't wear fancy shoes when I do that. It's very tough work. It's very rewarding. And we, in this case, you can see us drilling a coral core out of a living coral that's growing on the reef today. We don't kill the corals. We're not killers. We plug the hole back up. But this core comes back with us to Georgia Tech for analysis. And it will tell me about the climate history over the period that it grew. And I'll show you how that works. So this is a coral core here that we can see on in the white image there. And you could see that's the kind of core that comes out of the skeleton that I just drilled in the island there. And to the far right, you can see, or maybe you can't see very well, but the coral core contains layers, annual layers that go back in time. And they allow us to reconstruct climate as long as the coral was growing on the reef. So every centimeter to 2 centimeters, you have another year laid down by this coral record. And so the time that you drill it is the endpoint for your record, and the time that it started growing as a baby is the beginning of your record. And these corals are eyewitnesses to climate change. They have grown through the interval of climate change. They grew before the interval of climate change. And if we can construct a record that spans the length of time from the recent past over several centuries or millennia up to present, and we can place the current trends in a very important context. And it's important to remember that in this region of the world, nobody was sitting there with a thermometer in 1850 measuring ocean temperatures. I wish they were, but they weren't. We have no data from this area of the world prior to about 1900, and after that, just spotty measurements as a ship happened to pass by. That's what we have. So these records are telling us some very key information about a very remote region in the middle of the ocean that governs a large part of climate today. They go back 100 years. In this case, you can see this coral record I'm pulling out here from this particular core is about 100 years. It's about 1.5 meters tall or so. And we can go back 500 years. This is a fossil coral image from one of the same islands I work in. And we know it's 500 years old because we use radiometric dating, which is uranium, thorium, radioactive decay. And it's extremely precise clock. So that's how I know when these older corals grew, because they could look exactly the same whether they're 500 years or 5,000 years old. So we use this dating clock to understand when they grew. And we can date these rocks extremely precisely. In fact, I can date the rock to within 2 or 3 years. So this is our longest coral we've ever recovered from a fossil coral. It's about 2 meters long. It's worth about 90 years of information from 1319 to 1410 AD. How cool is that? I mean, this is a time capsule of climate information from a time period when we have actually no climate records that humans were making at all. This is my drilling assistant for scale there. Very excited. We also can push this back 7,000 years. This is the oldest corals I've ever recovered, and they look like this. They look exactly the same as the ones that were 500 years old. Okay, we use this radiometric clock to determine how old they are. And so what we do is we have to bring them back to Georgia Tech, and over a very long time period with a lot of hard work, we have to learn their language. In order to hear what they're saying, we must learn their language. And it takes a lot of effort because this language is in the form of geochemical changes in the coral skeleton. So we bring them back to Georgia Tech and we analyze them in my lab. And this is a mass spectrometer that I have in my lab. So it's a big kit, a very big, expensive kit, very finicky. My husband calls it my personal coffee maker. It blinks and I jump. It's the bane of my existence. It runs all day, every day, 24/7, all year. And that's not, I don't do that anymore. I have students for that. But I was there. And if it breaks, I fix it. So this is my student and I here in one of these lovely stage science photo shoots where, you know, there's day glow orange and laptops not facing the viewers and precariously posed on a stack of books. And I mean, this is just everything I love about science photography. But what you can see, there's some dose of reality. There's a nice healthy chunk of duct tape on this line here. So you know it's for real, okay, because we use a lot of duct tape in science. So this is where we put our samples. We take the core back and we actually drill every 1 millimeter. This is why we have to add up so many analyses. Every 1 millimeter down these meters and meters of coral, we drill a small amount of powder, and it goes into the vials that you see there, and it goes on my machine. And it takes 45 minutes to analyze one sample to the precisions that we need to make the measurement. What is the measurement? We are measuring the ratio of oxygen isotopes, the heavy isotope and the light isotope. And the ratio between the heavy and light isotopes that my machine gives me is a function of temperature, okay? It's locked into the coral skeleton as that geochemical signal. And I extract it on my machine, and if I measure enough of them, I can give you a monthly record of climate from any coral piece that you give me. And that's what I've spent the better part of 20 years doing. How good is this record of climate? I think it's probably the best paleoclimate record out there. And of course, I'm not exaggerating at all. But what we're looking at here is a record of coral geochemistry. You can't see the differences in color very much. It doesn't really matter because the curves look very similar. Over the 20th century. So there's two wiggles on this plot. One is a red curve of coral geochemistry. The second one is a black curve of instrumental sea surface temperatures measured in the region of my study areas. And what you can see is that they go up and down, but they track each other almost perfectly. The coral is recording temperature in its skeleton in this geochemistry that I measure in my lab extremely accurately. So this is a big green light for me to go crazy measuring the exact same geochemistry in corals from way before the instrumental record of climate began, so that we can place these current climate trends in context. This is the power of paleoclimate data. We have a calibration period, and then we have an application period that will extend our view of climate. 15 years of work. My first cruise to this area was in 1997, and I've been working diligently over the entire time since then to make the message from these rocks robust and make sure that people are listening and make sure that it's usable to the climate community as a scientific product. It has been a labor of love, but it's also been an obsession, perhaps an unhealthy one, as my husband can attest. I am truly obsessed with the sites and with bringing these corals' messages forward. And here's what you're going to see is over 40,000 individual data points on one plot. Okay, that's why the 15 years of work comes in at 45 minutes per sample. This is what we've been able to amass. It's far from complete. I have my whole life ahead of me to continue working on this. But what you're looking at now, the 20th century is compressed into the far right of the plot, and the time axis is extended back to 1000 AD, okay, using those fossil corals that we've radiometrically dated, so we knew when they grew. I've applied this exact same geochemical analysis to each of these fossil corals, and you can see them go back in time. Up on this plot means the coral was growing in warmer conditions. Down on this plot means the coral was growing in cooler conditions. And so what you see here is the climate goes up and down. It has a lot of variability as it goes through time, but what really stands out, of course, is that trend at the end of the record, the last 30 years. What your eye is seeing is a trend towards warmer conditions that began in the early 1970s at this site. It's quite clear. This plot strongly implies that the 20th century trend towards warmer conditions is unprecedented, at least in the last millennium. Okay, this is when I have the most data to bring to bear on this. And it really demonstrates that what's going on today is very, very unusual, and that these trends that are happening in this location, even though they took a while to transpire, are happening quite quickly. Okay, and so it would stand to reason that this trend will continue in the future unless we move to mitigate the greenhouse gas emissions associated with our energy use. So this is the power of the paleoclimate message. This is the power of the rocks. This is how they speak to us. They speak to us through plots like this, through amassing these kinds of data sets. They talk about climate change, where they've been. They talk about where we're going. And this is my message today. So if you don't want to trust me here in person, you can see it in Technicolor Charm on the Years of Living Dangerously documentary, which was, for me, a comedy of errors. It was a foray into no man's land, being in front of cameras and people saying, "What, you didn't bring any makeup?" Like, no. Not having the right clothes, is that all you brought? Yeah. I'm working here, people. But it was a lot of fun. It was a huge learning experience, and the people that I worked with were absolutely brilliant. So check it out. They did a great job despite my lack of talent and experience in this area. So the messages I have to you today are fairly simple. I hope I've communicated the benefits and the power of working with passion. And I love these research sites. I am literally in love with them. And every day that I go to work, I feel like I'm bringing purpose and power to those sites. I'm honoring them by looking at these rocks and trying to listen as carefully as I can about the messages that they are trying to tell me. And the other thing, of course, is the power of working with purpose. And I say this because not only am I passionate about climate change and passionate about what the records are telling me, but I'm also very keenly aware that these islands are very low-lying research sites. They are maximum 3 feet, 4 feet above current sea level. And so as climate change continues, they are being threatened by sea level rise over the next 100 or 200 years. That is not far in the future. And these places, the very places that I fell in love with, the very places that have provided us with these incredible climate records that help us to understand where we've been and where we're going with climate, those sites will be disappearing soon. So this is what drives me to get in front of an audience like you guys, try to inspire you, remind you that climate change is happening and that we have a chance as a society to do something about it. So I hope you agree that the rocks have spoken. How many people feel the rocks spoke to them today? Thank you so much.
That was awesome. Thank you so much. So we're going to do a Q&A with Kim. If you have a question, raise your hand. I'm going to kick us off with one question because I thought your point about 15 years of hard work and pouring into that one graph was so good for all of us to hear. And it sounded like you suggested your whole life will be in this work. And I don't know if everyone in this room feels like that's an unusual comment, but I feel like in today's society, you don't see someone who has dedicated their life to one particular exercise or discipline like that. So I'm curious to know, in your field, are there people that haven't made a similar commitment and you've seen that as a result in their work and their results? So maybe speak about like the benefits of having a commitment to your work from a life perspective.
Yeah, so I'm singularly obsessed. Most of my colleagues know this, and it's a approach I've chosen to take. Most people in my field, they jump from site to site to site to site, and they skim what they think is the gravy off of a certain site, and they publish that, and they go on to the next thing. What I've chosen to do is dig very, very deep, and I've tried to dig and get those diamonds of information that require the extra levels of investment. And what that has translated for me in terms of science is a much more robust data set that's much more widely used. So the investments are just now beginning to pay off 15 or 20 years later with papers that are hugely cited, data sets that are plotted in many of my colleagues' presentations when I go to international meetings. But that's 15 years of me just keeping my eyes on the prize and keep banging my head against that wall very single-mindedly. And I think it's paid off. However, I know that I got some reviews back at one point from one of my proposals on the coral stuff, and one of the reviewers said, one has to ask oneself, when is data too much data? I'm like, what? Of course, never. So in climate science, it's very hard to have too much data, and so the more I dig, the more I learn, and that's been my approach. Yeah, I think so. Oh, yeah. So the question was, how does my approach to my science translate into other things that I interact with or see in my environment? And I would think it does. I think I'm quite OCD, so I'm not afraid to say that. Probably many of you are too. And I can't sleep if there's something that's noodling me about my immediate environment. I also blogged once about fashion at a women's fashion at a scientific conference, and because I walk around that conference kind of dissecting people's outfits like a scanner, like, oh God, that's bad, and oh, that's good. And so I thought, I should blog about this. And I got tenure, so I can do that, because you don't want to do that pre-tenure. But that's the kind of thing that I like to do. So I did that. It's my most read blog post. If you search women's fashion at AGU, which is our marquee event as climate scientists, you will see my blog come up. It's been read over 30,000 times, which is approximately 10 times more than any other post I've ever written. So that's one example of the the aesthetic eye that I bring, and that I'm very passionate about fashion too. Yeah. Very good question. So why those sites? They're very small line of islands. In fact, they're called the Line Islands in the middle of the Pacific Ocean. Why those sites? We were interested in a climate phenomenon called the El Nino Southern Oscillation, which is a ocean climate phenomena that's naturally occurring every 2 to 7 years, and it's born in that very area of the world. And that's what I started studying as a sophomore in college for my summer internship. And I know that whatever I can learn about that will never be enough. It's one of those weirdly quasi-periodic, chaotic, mysterious climate events that occurs in our climate system. To me, it's just fascinating that that occurs. So I was trying to go somewhere in that vicinity. And there's a really long story involving more twists of fate as to why I landed at that particular site. But it involved toothless people bribing the yacht people and lots of alcohol. But we landed at this site called Palmyra Island, which is uninhabited. It's a US possession, so we could hide there from all the bribery going on in the island nation around us. I've since made friends with those folks, so we are on very good terms with all the island nation people. And we landed there, and that was the core of my research study for my thesis work. And as a faculty, I've expanded to the neighboring islands, and I've reaped the fruits of chasing this particular natural climate phenomenon. Thank you. Yeah. I think there's room in science for I just love science in general. So I think I love the science of space. In fact, we have a couple new space scientists at Georgia Tech. So for kids, it's extremely inspiring to think about space and that frontier, and there's probably many opportunities in that area in the future. So climate science isn't horribly funded, so my work has been fairly well funded, so I'm not one to complain. So I think, I don't know, I'm just a huge fan for all sciences, as the case may be. I know the space science program has actually suffered quite a bit of funding cuts lately, so my heart goes out to them on that. I think it's a loss. Yeah, so something that immediately leaps to mind is the fact that my mass spectrometer, when I got to Georgia Tech, was not purchased, but I purchased it. And I installed it, and it didn't work. And it just didn't work for like 1 month. It didn't work for 3 years. So as an assistant professor at Georgia Tech, and your main machine that you're relying on to generate the data that your career will rest on will not work. We sent it back to the factory. They shipped out another one. It didn't work. I changed vendors. There are only 2 in the world. I changed vendors. And they brought it out, and it didn't work. And so I think my husband can attest to a lot of deep breathing and a lot of hope and trust. Eventually, I did get the machine to work and have been playing really catch up ever since. But it's been the internal commitment and peace that my path is a sound one, my science is sound, and I just need to stay the course. So that's a really good question, because that was a pretty major obstacle. One might argue it could have derailed my entire career. And I think it speaks to Georgia Tech's commitment, because certainly my publication record is not what it could have been, and yet they still chose to tenure me and keep me around. Yeah. Yeah. Okay, so there was a lot of information on that plot. I'll just go back to the plot and talk to you a bit more about it. There's a lot of information here. This is monthly data plotted over the last millennium. So what you're seeing in terms of the spikes here that's not error. This is the natural climate phenomenon known as the El Nino Southern Oscillation. Warm are El Nino events, and cool are La Nina events that occur at this site every few years. And so this is the black envelope that you see here. And with respect to the y-axis, how much temperature is that worth? One of these individual warmings is worth about 1 or 1.5 degrees Celsius, roughly 3 or 4 degrees Fahrenheit. And what you see so that's the total amplitude of the black here. So you can move that over and look at the trend in the recent past. We know from doing an abundant amount of geochemistry on these corals, not only the oxygen isotopes, the light-heavy ratio of oxygen isotopes that I measured and that's plotted here, but we can also measure different chemistries having to do with the trace metal content of the calcium carbonate skeleton, and we can confirm that that trend over there that you see is roughly 3/4 of a degree Celsius or so. So, and we can confirm that through a variety of alternative approaches. So, is that significant? How significant is that? The global average over the last 30 years, the last 100 years is a relatively larger number, about 1 degree Celsius or so. So the tropics would seem to be rather late in responding, but they're catching up quickly, is what this data would imply to us. And this apparently, even though it's a relatively small number, it's a very large number compared to the variations that have occurred in the recent past. In terms of geologic significance, it's very important to remember that when the last glacial maximum occurred 20,000 years ago, the tropics only cooled, we think, by 1 to 3 degrees Celsius. Okay, that was the biggest climate change our planet has undergone in the recent past. And the tropics did a little small cooling. And what we're projected to do is do the 2 to 3 degrees in the tropics by 2100. So we'll do the flip side of that. In 200 years, the planet did 2 to 3 degrees cooling in this site over 10,000 years. So we are really climate change on speed for this planet. It's not, of course, not news to this crowd. One more? Yes? Thank you so much for that question. That's great. I do have 4 kids, and that's quite an optimistic statement in itself, actually. Trust me, 7 a.m. it looks ridiculously optimistic. But I am very, very hopeful. And for 2 reasons. One is because when I speak to children and young people, I see them engaged, and I see them passionate, I see them concerned. And that is great. It's much better than speaking to a room full of adults, actually, like, oh, that's kind of neat. Okay. No, kids really get it, and they look at you, and they're digesting everything you're saying, and it's resonating with them. So they're listening, and they care. The second reason is because I teach a class at Georgia Tech called Energy, the Environment, and Society, in which I challenge a bunch of college kids to get out there and make a difference. Like, literally get out there and reduce carbon footprints over the course of the semester. It's a competition I run during the class, and there's a prize, and it's teams, it's really fun. And they get out there and they offset my entire family's carbon footprint and more in 2 months. Okay, so they get out there and they do stuff that makes that level of difference in 2 months. The winning team will reduce carbon by up to 200,000 pounds over the course of 2 months. Okay? You let that sink in. The average American's carbon footprint is 30,000 pounds per year. Okay? So this gives me hope. There is a lot of low-hanging fruit, people. There's a lot in your lives. There's a lot in my life. There's a lot in our society. And if we can get systematic about identifying that and acting on that, we will be rapidly on our path to change. Efficiency is the cheapest and most easy thing to do. It'll give us a lot of benefit in terms of starting to tackle this problem systematically. So please look at your own lives and think about what's the low-hanging fruit in your life. Thanks.